I think there is noise coming from Michał.
Hi, everyone. So today is May 25th. This is a Batch Working Group bi-weekly meeting. This meeting is, as you all know, recorded and will be uploaded to YouTube. So please adhere to Kubernetes code of conduct. We have one item on the agenda today. Daniel from Google and myself will be presenting JobSet API version 0.1. We have a small demo as well. Daniel, I'm going to make you a co-host so that you can present.
All right, sounds good.
Take it away.
All right, let's see if I can share the right screen here. Let's just do this one. All right, can everybody see my screen, the slides here?
Yeah.
All right, cool. Let's do this. All right, still all good in presentation mode?
Yep.
Okay. All right, nice, we can get started then. Okay, cool. So yeah, as Abdullah mentioned, my name is Daniel Wegemeyer. I've been working with Abdullah on the JobSet API project the past few months. So today I'm going to be giving a brief presentation and a small demo of it. So yeah, just a quick outline of the presentation. I'm just going to start by discussing what problems we're actually trying to address with this project. Then just do a quick overview of the job set itself and how it attempts to address those problems. Do a quick demo and talk about some of the features available in our first release so far. And then just finish by talking about some future plans for the project. So what are the problems we're attempting to address here? So basically, we all know the job API is kind of like a go-to API for running batch workloads, but there's certain kinds of batch workloads that require a little bit of extra orchestration, configuration on top of the job API, which represents some kind of points of friction or like opportunities for simplification of the user experience. So one example of this is the need for multi-template pods. So as we all know in the job API, when you define a job, you only can pick one pod template spec, and all the pods created from that job are going to use the same pod template. So why is this a problem? Well, because in these kinds of distributed ML and HPC workloads, basically there's different paradigms, like a common one being like a leader worker paradigm, where the pods, there's actually different distinct groups of pods that may have like different behavior, different logic. We may want like different back off limits and retry policies. We may want different success and failure policies for them. They might even use different container images in extreme cases. So it'd be useful in order to be able to have multi-template pods. So just to make it more concrete, like in the leader worker paradigm, for example, the leader might be responsible for coordinating distributed checkpointing, while the workers are kind of more focused on the actual computation itself required for the forward and backward pass of each training step of training some like large language model, for example. Another kind of problem we're attempting to address here is network setup. So one very common requirement for these distributed ML and HPC workloads is the ability for pods to communicate with each other. As you might expect, they're doing these distributed computations and they need to be able to talk to each other directly in order to synchronize, accumulate gradients, whatever it is. And in order to do that, basically these ML frameworks require the user, they want to consume this information about where these pod network endpoints are in the form of an environment variable that passes just a static string listing the network endpoints. And so, this represents a problem because that means we can't just use the pod IPs and port numbers as the network endpoints, since the pod IPs are assigned dynamically. So then we have to use host names, and specifically we have to use deterministic host names that are generated by the index job, so that they are deterministic and we can define them in an environment variable in our spec. However, there's one more extra step that you need to take in order for the pod-to-pod communication via pod host name to work, and that is you have to actually deploy a headless service which selects these pods, and so that will trigger the creation of the DNS records needed for the DNS hostname resolution to actually work. And this is just another point of friction for the user. It might not be obvious to users, especially who are not heavy users of Kubernetes, maybe data scientists and so on. And we thought it represents a good, opportunity for automation. The third one here is kind of the biggest one, and unfortunately, one of the harder ones to solve is framework-specific configurations. So these ML frameworks, HPC frameworks, they are very like configuration heavy. They require all kinds of environment variables and metadata to be passed them, and sometimes they're well documented, sometimes not so much. And maybe you think you're interpreting the docs correctly and you're assigning the metadata in the environment variable, and you get some misleading error that will send you down some rabbit hole the totally wrong direction. And this is definitely a point of friction for getting these distributed ML workloads running properly. And we would love some kind of simplification to this process where the user doesn't need to worry about the ins and outs and needing to research every single cryptic environment variable in detail, understanding how this actually works under the hood, but rather can just focus on the fact like, I want to run a distributed PyTorch training job, and that's all they need to know. The fourth one is startup sequence. So in certain scenarios with certain frameworks, there's actually dependencies between pods. So for example, in MPI, the workers all need to be available and ready before the leader is, because the leader, the first thing it's going to do is attempt to SSH into each worker and start executing tasks on it. And so it needs those workers to be available, obviously. And on the flip side, PyTorch, the leader needs to be available first before the workers, because the workers, when they come up, are going to try to attempt to connect back to the leader is the first thing they do. So the leader needs to be available. So you need some kind of configurable startup sequence. And yes, most of these frameworks have some kind of like retry logic and timeouts, but those are, just like educated guesses and just hopefully tuned correctly. So it usually accounts for weird edge cases where there might be like weird discrepancies in the container image pull time between the leader and the workers, or whatever it might be. It'd be much better to have some sort of guarantee that whatever pod this pod is dependent on is definitely up and ready when we launch or create this new pod. And the last one is just there do exist solutions for these kind of distributed ML and HPC workloads like the Kubeflow training operator. However, it currently just has like multiple different job types, like a specific job type and different reconciler for each job type. As you can see, like a TF job, PyTorch job, MPI job. They each have different configurations and semantics, and we thought maybe there might be an opportunity for just unification here. So moving on to the job set. So the job set is our attempt to address some of these and at its core, a group of jobs as a unit, and modeling these distributed training jobs as a group of jobs rather than working at the pod level. And so you might ask, why do this? Like, why would we want to model a distributed ML or HPC workload as a group of jobs? Why are we moving up this level of abstraction? And for one, the main thing that it gets us right off the bat is addressing the first point of friction we discussed, which is the need for multi-template pods. Because with multiple jobs, each one has its own pod template spec. So you can define a special template for the leader and a different one for the workers. Maybe if you're using TensorFlow, you might have a third type, which is the parameter servers. So you have these distinct group of pods, and now you can truly define different specs for them. And yeah, as I kind of alluded to earlier, the kind of North Star here is trying to aim to offer a unified API for deploying ML and HPC workloads on Kubernetes. And I'd like the design doc and just a link to the API itself for anybody who kind of wants to get a direct look at some of the details here. Moving on to just a very high level abstract example of how the job set is structured and what it looks like when it's running. So here you can see the job set itself. Its primary feature is that it has a list of replicated jobs. So let's just quickly define what a replicated job is. A replicated job just has a job template, just a regular batch job, and it has some number of replicas for that job. So it can create one or more instances of that job from using the same job template. And these will be distinguished using a job index, kind of similar to how in an index job, there's like pod indexes, like completion indexes. The other feature has is this network field, which will allow you to do what I was alluding to earlier about enabling pod-to-pod communication via pod host names, just by setting a value in this network field, you can basically automate the creation of this headless service, get the selector set up correctly so that you don't have to think too hard and deal with weird networking issues when trying to enable this very common requirement of pod-to-pod communication via host names. So a job set, moving back up here, has multiple replicated jobs, and it also has success and failure policies. So success policy operates on one or more replicated jobs. So basically, the success policy is defining under what conditions will the job set be marked as complete. The default, if left unset, our webhook will just default it to applying to all replicated jobs and all their jobs. So basically, every single job created by all replicated jobs need to complete before the job set will be complete. But you can kind of narrow that down. It's configurable. You could say if this left replicated job here is for the leader and the right is for the workers, you could say make sure you could say all jobs in the leader replicated job are complete before marking it complete, but we don't necessarily care about the workers, for example, because different frameworks have different semantics. So some might require that all the workers complete before the training job is actually complete. Some might require the leader is complete, and that's how you know it's done. So it's configurable in that sense. Failure policy is similar. Right now, the only supported failure policy is when any job fails, all jobs will be restarted. Just because this is pretty much a very common paradigm in these distributed ML and HPC workloads where there's some kind of distributed computation going on, and if one worker goes down, that state is lost, and the simplest solution is simply just to restart everything, load the most recent checkpoint and resume training, rather than deal with weird distributed systems issues that can probably arise when trying to recover state of like one specific worker that's dependent on the outputs of other workers and so on. And it also, the failure policy has just basically a max number of restarts. So you can say, okay, how often can this, or how many times can this happen, this job set restart on a failure? And like you can define 0 times, 1 time, 2 times, so on. And yeah, there's a headless service we talked about, maybe set up by one of these networking fields that I mentioned earlier. So that's kind of just like a very high level. These isn't all the features and fields, but those are just kind of some of the main ones I wanted to call out. So now we can kind of look at some more concrete examples here. Let me open this link. So this is an example of a distributed PyTorch training job for just a handwritten digit classifier using the MNIST dataset. So kind of like the canonical machine learning toy example. Here's the spec. As you can see, it's pretty simple. There's some defaulting going on under the hood as well. So you can see we're defining our job set here. It's named PyTorch. Here's our list of replicated jobs. We only have one. It's called workers. We only need one in this case because PyTorch actually defines the worker as rank 0 as the leader automatically. So we don't necessarily need to have a separate replicated job with a separate spec for this one. We could, if we wanted to have some special handling for this leader, depending on what our goals were. But for this like very simple toy example, it's not necessary. We're also not seeing here some defaulting going on. So for example, our success policy is being defaulted to target all replicated jobs and all the jobs in those replicated jobs. So basically all these will have to complete before this training job is marked complete. Also the failure policy, or not the failure policy, sorry, restart policy is being defaulted to on failure, and the job completion mode is being defaulted to index. So as you can see, we're setting our parallelisms of completions to 4 here. So 4 workers. And then here's some of these environment variables I was talking about earlier. For PyTorch, it's pretty simple, luckily. So we just have our master address and port number. That'll be like our leader. You can see the format here. The host name we generate is the job set name dash replicated job name dash job index, right? So there's only one replica of this replicated job, so it's index 0. Then the pod index from the index job, and that's also 0 for, we're using rank 0 for the leader. And then dot, and the subdomain is the headless service, which is also being set up behind the scenes. If left unspecified, that networking setup, it will default to setting up the headless service and enabling the pod-to-pod communication via hostname, just since it's such a common pattern. And the subdomain will be set to headless service name. So here you can see this headless service name is the job set name dash replicated job name. And then, yeah, here's our torch run command, which is just utility for running distributed PyTorch training jobs. And yeah, so I guess now I can just do a quick demonstration. So let me just, you can see we'll just install our job set here. So this is just the installation docs on job set. I'll copy the command. It's just one command. And I'm already connected to my cluster, so I can just install it. Only takes like 1 second to install. It's very fast. It's nice. Then I'm actually in the repo already, so I can just apply the PyTorch example from here directly. So I'll do apply f examples, PyTorch, and mnist. Okay, it says our job set's created. So let's say get job sets. And there's our job set called PyTorch, and do get jobs. You can see there's our PyTorch workers that job index 0 I was just mentioning earlier. We've got our pods, and as you can see, there are 4 pods. They're all running. And let's open one up and take a look at the logs. Here we can see it's on epoch 1. It's training. Our loss is not monotonically decreasing, but overall it is going to be decreasing. I'll let that run for a second, and it should kind of converge at some reasonable accuracy by the end. But yeah, and let me open up a new terminal here. There's also this other example I wanted to look at really quick. That's pretty cool. It kind of shows off our failure policies. So yeah, so this is a different job set. And in this case, we're actually defining a failure policy, which I did not do for the PyTorch example. But basically, we're saying on failure, restart all jobs up to 3 times. So what this example will do is we actually have 2 replicated jobs. I just named them leader and workers, even though they're not really doing anything in particular, just to kind of highlight the concept. So basically what this bash script will do in the leader job is it will arbitrarily have the pod index 0 just exit after 10 seconds. And then basically our job set controller will detect that the job has failed because we set the backoff limit to 0 in this example so that this pod fails, the entire job fails. That means the job set controller will detect this and it will kick in its failure policy of restarting all jobs, and it will do so up to 3 times. So that's kind of how the failure policy works. And here's back to our PyTorch example. You can see, okay, it finished training with this accuracy of 97%, which is passable. So that's the PyTorch example, and I'll just go ahead and delete the PyTorch example now so that we can apply this other one, which is kind of cool. This is under simple, and it's called failure policy, I believe, or no, it's called max restarts. Yeah. So yeah, here we go. So as we can see, here's our 4 pods for the failure policy. There's the 2 leader pods, and here's the 2 worker pods. And after roughly 10 seconds or so, we should see 1 error. There we go. And then, okay, so that was fast. So you can see here errors. And then you can see immediately after, the 4 pods are terminating, and then 4 new ones are being created. And if we go to describe job sets, then failure policy, we should see, yeah, the restart attempt here. So you can see it restarted once, it restarted again, and then should restart the 3rd time. There we go. So there's the 3rd time, and that's the last time it's going to restart. And then eventually, it'll fail, and then the entire job set will be marked as failed. So yeah, that's kind of how it works. Those are the just small demos I wanted to do. So I guess we can move on. So yeah, these are the features. Let me present again. How do we? Oh, here we go. So we just had our first release 0.1. We're up to 0.1.3 with a couple of bug fixes. But yeah, these are some of the features. I kind of have already discussed all of them, or most of them anyway, so I won't go over them all in detail. But yeah, we support the replicated jobs, creating multiple jobs from the same template, the networking setup, so enabling communication via pod host names. Exclusivity is one we didn't touch on yet. Basically, that's just support for assigning like a 1-to-1 job to topology domain assignment. So that just means you can have 1 job per node pool, 1 job per zone, 1 job per server rack, and they can exclusively run there. And this is particularly useful for certain running certain kinds of workloads that require like hardware accelerators, which might have high bandwidth network links in between the hardware accelerators, and you really want your pods that are part of the same job all specifically on that topology where those hardware accelerators are connected and available, and then a different job on a different one, and so on. I don't want to do like a deep dive on hardware accelerators right now, but that's kind of one use case. And then, yeah, the default success policy, default failure policy I talked about, the custom failure policy, I just kind of demonstrated that. Then, one thing we didn't talk about too much is the support for suspending and resuming a job set. Yeah, that's available as part of our first release in the Alpha API. So if you suspend a job set, it will in turn suspend all those jobs. And if you resume it, it will resume all those suspended jobs. And that's going to be part of the queue integration we're working on, which I'll discuss later. And then, yeah, we have a defaulting and validation webhook to kind of simplify and make a better user experience. And then we have some SSL related features for, you can use just an internal cert without thinking too hard, or you can use Cert Manager if you want, if like cert rotation is a priority for your company's security policies. And yeah, some of the future plans for the project, one main one is integrating with Q, which we are actively working on right now. We're also looking to have better support for MPI, which is kind of a tricky one. It requires some like SSH setup and secrets and some configurations. So we're hoping to add some automation there. We're also trying to develop some system for supporting these the automatic configuration of framework-specific like environment variables for popular ML and HPC job types. And this is just a tricky one. We've been kicking around some ideas, so yeah, those are kind of the future goals of the project. So yeah, I think that's everything I had. Thanks everybody for joining the presentation, and if you have any questions for myself or Abdullah, feel free to ask or reach out on Slack.
Thank you, Daniel. Any questions?
Looks like Diana has her hand raised.
Yeah.
Oh, yeah. Thank you. Thank you very much for going through that. It's really nice to see multi-pod template artifacts. I have a few questions. So, can you share a little bit about why we chose using a different resource definition versus like adding all these features into the current job API? What was the decision making on that? And then the other thing was I wanted to know, you talked about the service configuration. Is that something that's in the job set where you define what that service is, or do you have to set that ahead of time and then reference it in the job set? I had a third question, but I can't remember it now. So,
no worries.
Sorry.
I think on the first point, Abdullah may be able to speak to this in more detail, but I think we chose to use the CRD just for like velocity's sake and for getting a prototype and Alpha API up as soon as possible, and rather than working the upstream job API where there would be much more scrutiny on the changes we're making, and also I think some aspects of the job API, it'd be a really big change, I think, to support multiple pod templates in one job. I'm not sure how feasible it is. Maybe Abdullah can chime in on that as well.
Yeah, it's in general like related to the concept of separation of concern. So the job API provides really good interface or API for managing a group of pods of similar template. And so like the natural way of evolving this to multi-template is basically to compose multiple jobs. Ideally, in the future, we would be able to push job set itself upstream. And it would be the canonical, way of creating multi-template jobs. But in any case, like you need something, like whether it's in the job API or something outside, to manage these different types of jobs, right? And so it's a design choice. Aldo?
Yeah, I have a comment on that exact topic. Another point is that today we are working on the job backoff per limit, and we were discussing some scalability limitations. So kind of like one job can only handle so many indexes. So actually having another job set, having a job set allows some kind of slicing or partitioning. So that if you have such a big job, you can split it into multiple jobs and you can easily manage them through one job set. So it comes neat as a neat solution to have this hierarchy of jobs instead of pushing it all down to the job API.
Okay, I get it. Thank you.
I think
Yes,
you had one other question about the service, if I remember correctly, the headless service.
Yes.
So you're asking if it was like on the job set level or replicated job level, or what was, could you repeat it?
The question was, is that I saw that there was a reference to service, but I didn't know if you defined that definition of the service in the job set, or do you set the service up? You define the service, create it, and then reference it in the job set.
So we actually don't, the user doesn't need to define or reference the service really at all. It's all just handled under the hood. So in the network field,
Okay.
there's just basically a Boolean value set enable DNS hostname. If you set it to true,
Okay.
then the controller will create the headless service and configure the selectors to select the correct pods and everything. And so the user doesn't really have to think about it.
The idea here
Okay.
is again like to provide like like the service itself from our perspective is an implementation detail. The semantic is I want the job to have pod-to-pod communication.
Yeah.
And so that's why also we're not exposing like the knobs of the service itself, because
Gotcha.
Yeah.
Okay.
it's an implementation.
I did remember my third question. I get, yeah. So you're really just defining it under the covers. So that sounds good.
Sorry?
I do remember my third question. That was I wasn't quite clear about what happens in the failure scenario, but if you had two templates and if you dispatch those two batch jobs from those templates, and you set a failure scenario for, let's say, the first one, and it meets that failure scenario, what happens to the pods that were created in the other template? Are they terminated as well, or do they stay running?
Well, right now, in that case, the failure handling would just restart all jobs, and so by extension, all the pods, up to whatever the max restart limit is you've defined in your failure policy. And when the job set itself fails, eventually, I think since the controller, has like an owner reference to the job, if that one's still running, I think they would end up being killed as well. I'm not, maybe Aldo or Abdullah might understand the edge case a little better. They have more experience with the job controller. But yeah, that's what sorry, go ahead.
Yeah, are you asking about like, so the semantics here is that if a pod fails, well, actually job set doesn't care about like pod level failures. It looks at the job level failures. Pod level failures are handled by the job API. So your failure policy is really set at the job level. Like if replicated job fails, then do X, like fail everything else or restart everything, all other jobs. Now it's the job API that decides when a job fails. So if you set backoff limit to 0, it means that if any pod fails, then the whole pod is considered failed and so on. I have to recreate the whole job at the job set level.
And then when you meet the criteria of failing the full job set, if you had two different batch V1 jobs and two different job replicas, or I'm sorry, I can't remember the name of the field, but basically two templates, right? And you're setting the criteria for one, maybe I'm make sure I want to understand this right. But you don't set it for the second one. You meet the limit, and basically the job set's going to fail. What happens to that other template? Does it still stay running, or do you force that other job, a batch job, to fail as well, and the pods get terminated or deleted?
But that's like you can decide that at the failure policy, right, in the job set level. Because
Okay, so if you
can
want,
decide, yeah, go ahead.
go ahead. If you want the other set of replicas to fail as well, you have to somehow link it to the first, I guess, job set. Not
I
sure I'm
mean,
explaining.
well, within the set, you said you have two templates, and the semantics you want, if template one fails, you want the other one to fail as well, right? Is that what you?
Yeah. Yeah, I was wondering what the behavior is or what the design is for that.
Right. I mean, the failure policy decides like when do we declare the whole job set as failed? It's right now if any job fails, I guess that's like there's all and any. So if any job fails, the whole set is failed.
Okay.
The other semantic is if all jobs set fails, like we're gonna fail the whole job set. And then there is also part of the job, the failure policy. You want to decide, okay, when, like, how to. There's like max restarts, right? It's like the back of limit.
Right.
So how do I deal with that? You say, okay, if any job fails, then the current policy that we have for restarting is recreate all. Basically, we're going to recreate all the jobs. Basically, force restart them.
Okay. And then, so but when you meet that criteria, when you get to the end and you say, we're not restarting this anymore, and one of the templates failed for some reason, right?
Okay.
What happens to those other templates, right?
I don't actually. I think we declare the job set as failed, but they continue to run the other ones.
Okay. Okay. Got it. Okay. Thank you.
But I guess the point there is that those will, if not configurable today, they will be configurable, right? Those policies.
Yeah. Correct.
Okay. Thank you.
Thank you, Dan. Abhishek?
Yeah, thanks for presenting. I mean, I have a community question. Um, Maybe it's related to what we are describing. So this is definitely a useful feature, but then communities. I mean, I can speak for Ray. So CubeRay has this project that has invested heavily in their own controller and own failure policies and restarting and whatnot. So what would be the direction for that community if they want to use it? Do they stop developing Kubernetes and then move to JobSet? So I would like to hear your thoughts on that.
Yeah, that's a very good question. I don't think we will get to the point where everybody is going to converge on one API. I think Ray has a lot of. We looked at Ray, tried to basically find a way where we can integrate. But the Ray semantics have a lot of like, you want a lot of like specific custom logic to handle Ray workloads. It's tightly coupled with the Ray framework underneath. They have auto scaling and other specific, setups.
Mm-hmm.
It's not about job sets. Even like we can't even map it to a job API. So that's one. The other thing is like, as I mentioned, the goal is not to really try to like converge everybody. We're trying to converge most, at least. So we found, for example, most of these like, training operators that we have in Kubeflow, those can be replaced by JobSet, for example. Anything that you are deploying directly on Kubernetes will probably work fine with JobSet, but APIs that tries to basically integrate an orchestrator with an orchestrator, I will always find it a bit hard to do. Like Spark is another example.
Mm-hmm.
There's a lot of custom logic around it that will probably, it's probably best for them to have their own API. So that's
Yeah.
my take. I and it's not a like it's not a limitation. It's actually the opposite. Like Kubernetes offers us this really great way of extending the API. So so that's a great feature, um, and we should continue that path. Like if it fits, we do it. We're not going to force it, right?
Okay. Okay. Thank you.
Aldo?
So in the same topic, my take would be we should try to go as far as possible in terms of converging. Uh, in the case of Ray, even if it's not possible to converge at the job set level, maybe it's still possible to converge at the job level. And that's where it's useful, one, for the Ray community to stay engaged with us, with the working group. So we can push the features that in job that might be necessary to cover race use cases. Uh, so yeah, that would be my perspective as a job, one of the leads in the job API. Mm, so yeah, very happy to have you here, Abhishek. I hope we can continue uh,
Yeah.
discussing these topics. To
Yeah.
be honest, I'm probably less familiar than Abdullah on what Ray is doing. Only only 2 days ago, I learned that there were multiple templates
Yeah.
within a Ray cluster. Um, so yeah, at least it will be very useful for you to at least learn about the limitations we have, uh, all the all the problems we have run into throughout the years, like losing track because of garbage collection, or scalability limits, or API based practices. So yeah, it will be really good for the Ray community to stay engaged and follow all these discussions about API and scalability and whatnot.
Yep. Yep. Sure. So maybe, I mean, you can term me as an insider. I attend Kubre community meetings and I have interest there. So yeah, I'll keep you posted about requirements. But net, I mean, it's a very custom approach that they are that the community is taking. The Kubre has its own API server, and it really boils down that they want to control the fate of the pod via the Kubre operator. So as Abdullah said, it's really custom logic, and for them, it's not about spinning pods, but once a pod is spawned, it's more about sending ray tasks which are like Python jobs on those workers. I mean that's an interesting use case for them. So in terms of scalability, it might not be as big as some of the other use cases that we are seeing, but growing and shrinking is something more useful for them.
Right. Yeah, I'm just doubling down that um, particularity, like with these same thing with Spark. So it is pretty much like an orchestrator, like a resource, and for them, pods are basically workers, like I
Hmm.
mean machines.
Yeah.
And they already have a lot of custom logic related to managing those workers, whether they being pods or nodes or whatever, like the lower level orchestration that they deploy on top. So I don't want to be like dismissive and say it's not going to work, but I see challenges here. It's exactly what you mentioned. They want to control the fate of the pod, basically control the fate of the node, because that's actually part of what this framework is actually offering as an orchestrator. So,
Okay.
for example, they want to pick, like when you downscale, they want to pick the exact pod that they want to downscale.
Yeah.
And yeah.
So yeah,
that's,
yeah. Thank you for those comments. I mean, sorry for chewing up a lot of time, but interesting. Yeah.
But as Aldo mentioned, we should continue to try to engage and find some common ground. Again, I don't want to be dismissive and say like it's not going to work. We should continue to try and converge.
Yep. Sure. Yeah. Thank you.
All right. Any other questions or comments? All right. Thank you so much. Thank you, Daniel. We're almost at time. And see you again next couple of weeks.
Thank you.
Great. Thank you, Daniel.
Thanks everybody for coming.